We will now discuss about how FFT is useful for DTMF detection, and if you are using FFT for DTMF detection, what limitations are there. Let us discuss about them. But before that, here we should actually look at the list of the frequencies. Okay, so this is a hex keypad. Okay, so these are the 16 keys that we have considered for our design. So these 16 keys is 1 2 3 4 5 6 7 8 9 star 0 hash ABCD over here. This is what we have considered. These are the row frequencies in hertz. So 697 hertz, 770 hertz, 852 hertz, like that. These are standard. This is standardized by a body, so we are simply following it. Okay, so and column frequencies are 1209, 1336, like this. Okay, now here for our design we have considered actually a sampling frequency of 5000 hertz sampling frequency. So here one should recollect the fundamentals of FFT and the relationship between sampling frequency and FFT output bin to bin separation. So FFT has n point FFT. If you are talking about n point FFT, let's say the inputs are coming at a sampling rate of Fs. Okay, if inputs are coming at a sampling rate of Fs, then the n points in the frequency domain, okay, if the difference between each frequency point that is Fs by n, means if you have, let's say this is actually your frequency bin 0, this is a frequency domain, so k is a frequency domain index. Okay, this is not apparent, so I will redraw, and this is a magnitude of FFT. Okay, so here if you are not clear, you go back to the fundamentals of FFT. FFT is computed, k is equal to 0, 1, 2 up to n minus 1. For each k, n is equal to 0 to n minus 1, x of n e power minus j 2 pi k n divided by capital N. So this is the FFT equation. So for each k we have to compute this whole equation. So like this we will be getting total in the frequency domain. So in this graph, if you see in the frequency domain, you will be getting n outputs. So FFT, an endpoint FFT takes n time domain values and gives n frequency domain values. Okay, so n frequency domain values 0, 1, 2, 3, 4, like that up to n minus 1. So what is significance of this each particular k value with the true frequency? If you want to discuss, then you must understand what is the frequency resolution. So frequency resolution in FFT is Fs divided by n. What is frequency resolution? The frequencies that you are able to resolve, the frequencies, that variation you are able to measure or you are able to observe. That's a frequency resolution. Means if this fellow corresponds to 0 hertz, okay, then this fellow will corresponds to Fs divided by n hertz. The next corresponds to 2 into Fs divided by n hertz. Let's take an example so that easily we can understand. Fs is equal to, let us say, 5 kilohertz. Okay, and n is equal to 64. So your frequency resolution comes to be, so 5 kilohertz means 5000 divided by n is 64. So 78 hertz approximately. So 78 hertz. So this first one corresponds to 0. So let us say at the bin number 2 you have got some value, the magnitude of the complex number. Remember here FFT output is a complex number, its magnitude what we are measuring. If its magnitude value is, let us say, assume some 40, okay, then what it means is, what is the meaning of 2? 2 means actually the true frequency is 2 into this frequency resolution, that is 2 into 78 hertz, means 156 hertz. At 156 hertz we have energy of 40. That's what it means. Coming back to our discussion, since our frequency resolution is 78 hertz approximately, so 0th bin corresponds to 0 hertz, first bin corresponds to bin, this is called bin, okay, bin, bin, I mean, or you can call as the index k, okay, anything will do. So first bin corresponds to 78 hertz, second corresponds to 2 into 78, like that. Okay, now coming back to our discussion, in the context of DTMF, where these are the frequencies,